Okay, so what I've written down here are the Feynman rules in a normalized perturbation theory. We wrote these down at the end of the chapter on renormalization. And I think that the only Feynman rule here that may be a little bit tricky is the rule for the counter term. So on the first line, we've got the rule for the propagator. Well, you'll derive that as you've always derived the rule for the propagator. And perhaps maybe let's just relate things. So this rule for the propagator would come from those two terms inside the Lagrangian. This term over here gives you the rule for the vertex. Then the rule for the coupling constant counter term is coming from that term in the Lagrangian. And finally, perhaps this is the most trickiest one to derive. The terms that are underlined in red give us that counter term. So that was one of the things that I wanted you to check. The only difference now compared to what we had before is that we've set the physical mass to 0, but that's really no big deal, okay? So please make sure that you are comfortable with deriving these Feynman rules. You know everything that you need to derive them, and it's a good exercise. Great. So if I now want to calculate G2 to one loop, what do? Well, so let's say I'm going to calculate in momentum space. So let's say G2 of P. What would this be equal to? Well, let me draw the Feynman diagrams. So I would have the tree. Then the first loop diagram that I could draw would look like this. And then I mustn't forget the counter term diagram. Okay. Let's just write down the expression for these diagrams, and then we'll make a few comments. So for the tree diagram, we just got I over P squared plus I eta. The eta is infinitesimal, it just shifts the poles so that things are well defined. And I'm using eta instead of the more usual epsilon, because we're going to use dimensional regularization. And in dimensional regularization, we use epsilon to denote d minus 4, the number of space-time dimensions minus 4. For the loop diagram, well, this is minus 12i times the physical coupling. Here, I have already written in the symmetry factors and all the rest, so I'm not laboring that. You know exactly how to do that. P squared plus I eta, I'll have an integral in 4k over 2 pi to the 4. I'll have an I over k squared plus I eta, and then the second line, the one after the loop, 1 over p squared plus I eta. And then finally, I've got the diagram that corresponds to the counter term. So I've got a propagator, I over p squared plus I eta. Then I've got the counter term rule, I p squared delta z minus I delta m squared. And then I've got the propagator after the counter term, I over p squared plus I eta. Good. Now, let's put h bars back into this formula, at least the relative h bars. So I'm imagining that the first term is order 1. That's the classical term. If I was going to put h bars back, well, we know the loop diagram would be 1 power of h bar down compared to the tree. And since I'm normalizing things so that the tree is order 1, the loop diagram has to be order h bar. So that's where the h bar would sit, okay? The relative h bar. So the loop term is down by h bar compared to the leading term. In fact, the counter terms would also have an h bar sitting inside them. So what would be involved here? Maybe, it's not the full counter term that would appear. If you think about the full counter term, so let's think about delta z, for example, it would have a piece that's h bar, let's call it delta z1 maybe. It would have a piece that's h bar squared, delta z2, and so it would continue. And the only piece that would contribute in this formula would be the delta z1, okay? So I'm not making that explicit here, but you can think about it like that. Actually, let's just make it explicit, okay? That's okay. So let's put a one there. It's the h bar piece of the counter term and the h bar piece of delta m squared too. And of course, delta m squared would have a very similar expansion. It would be h bar, there'd be a contribution, and then there would be h bar squared and another contribution. And this would be an infinite series in h bar. You would fix these terms by applying the matching conditions at each loop order. The counter terms are always determined by the matching conditions. So here we are now going to use the matching conditions to fix delta z1 and delta m squared 1. Which matching condition are we using? Well, it's pretty obvious which one. Let's just remind ourselves which one it is. It's going to be this one, that the 2-point function must be I over p squared plus I eta at p squared is equal to minus m squared. Good. So we'll use the matching condition to fix delta z1, delta m squared 1. And we are going to work to order h bar. So what that means is I'm going to rewrite this expression that we got here. And I don't care if the new expression differs from this old expression up to terms of order h bar. And the other thing that I'm going to have to do, I'm going to have to use dimensional regularization because it looks like this integral is going to be infinite, okay? So this is all, if you like, a bit of an aside. I'm not going to keep the h bars in place anymore. But what I can do now, I can write the following. Well, okay, let's keep the h bars for a little bit longer, maybe. This expression above can be written as I over p squared minus 12ig, an integral. Now I'm writing integral d dk over 2 pi to the d. I've already gone into d dimensions because I'm using dimensional regularization. And then I've got 1 over k squared minus, and now I'm putting in an m squared, okay? Let me call it m squared. Let me put a tilde underneath so that you don't think it's any m that we've introduced previously. And then we've got plus an I eta. We'll talk about that in a moment. Why did I do that? And then we've got plus, we've got p squared delta z1 plus delta m squared 1, and then plus I eta. Okay, so that's the answer. Okay, oh, that doesn't look good. Let me just do this. Yeah. Sorry, guys. I'm really making a meal out of this. Let's do better as we can. This should be the p squared delta z1 plus delta m squared plus I eta. And good, that looks better. Okay, so that's the answer that we get. Now, let's just sorry, guys. Okay, that looks better. Great. Okay, now if the h bars were put in, let's just put the h bars back. We would have an h bar sitting over there, we'd have an h bar sitting over there, we'd have an h bar sitting over there. Okay, let's make a few comments. First of all, you've done manipulations like this in the past. I claim the last equality above this box is equal to the equality below the box up to terms of order h bar. So if you don't remember what we did, or you're struggling to reproduce that, just take this formula below the box and expand it to first order in H bar, and you can verify that it's actually identical to the expression sitting just above. Good. Actually, I may have screwed up the sign. I think I did screw up the sign. No, did I? No, I didn't. Good. So yes, indeed, good. So this is correct. So make sure that you can reproduce that. Then, so that's the first thing. Then we're working in dimensional regularization. So we've got a ddk over a 2 pi to the d. So that's fine. That'll make sure that the results are finite. And then finally, why did we put this green m tilde squared in? Well, I've put that in so that I can use the tables at the back of Peskin and Schroeder, okay? And if I use those tables at the back of Peskin and Schroeder, they have a non-zero m squared appearing in them, and that's why I put this m squared here. What we will want to do, we will take m tilde squared to naught. So what we should do is, let's look up in the back of Peskin and Schroeder, and let's write down what the answer is. And after we've used the table in Peskin and Schroeder, let's set m squared is equal to 0. And once we've done that, we can take d to 4. So I'm going to write down the answer for this whole integral over here, just looking up the table of integrals at the back of Peskin and Schroeder. I'm including the minus sign sitting over there. And what do I get? Well, I get minus 12g over 4 pi to the d. And then I have got gamma to the 1 minus d over 2. That gamma function becomes a gamma of naught when d is 4. So that's the divergence from this divergent integral. And then we've got m tilde squared. And this is raised to the power of d over 2 minus 1. So please check that you can do this. I'm just using the tables inside Peskin and Schroeder or any other integral tables for dimensional regularization. It's fine. They'll all agree. And what we can see is this is equal to 0 for d over 2 minus 1 positive. And if we work close to 4 dimensions, well, then d over 2 is close to 2, and 2 minus 1 is certainly positive. So, in fact, the integral vanishes. So after using the integral tables, we get a nice simple result. We find we'll have I over p squared plus p squared delta z 1 plus delta m squared 1 plus r. And now we say, well, this thing had better be equal to I over p squared plus I eta at p squared is equal to minus m squared. That's our first renormalization. That's our first matching condition, okay? And so when we set that equal, well, we can see immediately that this means, okay, it's a little bit of thinking, but I'm sure you can do this, no problem. It means that we get delta z is 0 and delta m squared is 0. So, good. You should really set p squared is equal to minus m squared in both expressions and compare. And then you should really set, you should take a derivative of both expressions and then again set p squared is equal to minus m squared. And that gives you 2 different equations. And you can show that delta z is 0 and delta m squared is 0. So good. So what we've learned is the 2-point function is equal to I over p squared plus I eta to 1 loop. So no correction, no correction. This is what G2 was. Okay, now let's plug it into the Cullen-Samanzik equation. Okay, so the Cullen-Samanzik equation says m d G2 dm plus, now we'll have the beta function, d by the physical coupling GP onto G2. And then plus, now remember, if we look at Cullen-Simonzik, we've got plus n gamma. Here, n is 2 because we're studying the 2-point function, so we would have 2 times the anomalous dimension times by G2 is equal to 0. Now, take a look at our 2-point function. It is quite obvious that it doesn't depend on m. So this term over here is equal to 0. It's also obvious that it doesn't depend on the physical coupling. So this term here is also equal to 0. So what we learn is 2 gamma G2 is equal to 0. And since the Green's function itself is not 0, that means gamma is equal to 0, 2, 1 loop. So we figured out that the anomalous dimension vanishes to 1 loop. This was an honest calculation in a normalized perturbation theory. I hope that you can fill in all of the details. The fact, okay, so let's just talk about a few things. The fact that the counter terms vanished is unusual. So this is not usual. It's unusual, okay? So the fact that the mass counter term vanished at 1 loop is a consequence of the fact that we're dealing with a theory whose physical mass is 0. If you were studying a theory with massive particles, even at 1 loop, the mass counter term would not be 0, and you would get many other contributions to the counter terms at higher powers of h bar. At higher powers of h bar, delta m squared will not be 0, even in this massless theory. For the wave function normalization counter term, so at 1 loop it vanishes, and even if the physical mass was non-zero, it still vanishes. But at 2 loops, you will get a non-zero answer. The fact that it vanishes is a special feature of this 5-4 interaction. If, for example, you had a scalar theory with a 5-cubed interaction, then even at 1 loop, the wave function counter term would be non-zero, and you would have some non-trivial renormalization of the field strength. Good. Okay, so now we would want to generate the, we want to study the 4-point function and use that to determine our only unknown, which is the beta function. And we'll see that in 5-4 theory, the beta function is non-zero. Let me just stress again, at every single loop order, at every power of h bar, you will usually have a non-zero contribution to your 3 counter terms and to your beta function and to your anomalous dimension. Good. Okay, let's now turn to calculating the 4-point function and determining the beta function.